Every night, without quite knowing it, you walk past them. The stars you have seen 1,000 times, the ones visible on clear nights through your window, or from your backyard, or from that dark stretch of road between places. Each of them a sun. Each of them, in all likelihood, surrounded by planets. And some of those planets, right now, tonight, while you lie here in the dark, might have oceans. You have been living your entire life beneath a sky full of worlds, and for most of human history, we had no idea. The night sky looked the same as it does tonight. The stars burned with the same cold light, but we thought the space between them was mostly empty, mostly just distance and silence and the occasional piece of rock. It isn't. The sky above you is full of worlds, hundreds of billions of them in our galaxy alone. And of those hundreds of billions, scientists have estimated that at least 300 million sit in the region around their stars where liquid water, the ingredient that life, as far as we know, cannot do without, could exist on the surface. 300 million chances for an ocean, 300 million chances for rain to fall on a rocky surface, 300 million chances for whatever happens after water and rock and energy are given enough time together. Welcome to Sleepy Science Stories. I'm glad you made it here tonight. This channel exists for exactly this kind of discovery. The ones too large for a headline, too nuanced for a news segment, too extraordinary to rush. The ones that deserve to be absorbed slowly, in the dark, on the edge of sleep, when your mind is open enough to let something truly vast inside. Tonight, we're going to take the number 300 million apart. We're going to understand where it came from, what it means, and what we have found out there that makes it feel less like an estimate and more like a promise. We're going to visit worlds that JWST has looked at and found something unexpected in the light. We're going to sit with what it might mean, not scientifically, but personally. If the answer to the oldest question we have ever asked turns out to be yes, get comfortable, let your body settle, take one slow breath. The sky is full of worlds and we are going to spend the next 2 hours exploring them. For the entire span of recorded human history, we did not know. I want to stay with this for a moment because I think it is genuinely remarkable and we move past it too quickly. Every human being who ever lived before 1992, every philosopher, every astronomer, every person who lay on their back on a dark night and looked up and wondered, did so without knowing whether a single other star in the sky had planets. They suspected. Some argued fiercely for it. Giordano Bruno wrote in the 16th century that the stars were distant suns and that each might have its own worlds, a view considered so dangerous that it contributed to him being burned at the stake in 1600. But suspicion is not the same as knowledge, and the distance between us and even the nearest stars made direct knowledge seem permanently out of reach. The nearest star to our sun, Proxima Centauri, is 4.2 light-years away. The light we see from it tonight left 4.2 years ago. A planet orbiting that star would be, from our perspective on Earth, as faint relative to its star as a candle held next to a stadium floodlight, seen from the other side of the country. Not just hard to see. For most of our technological history, simply impossible. So for thousands of years, we looked at the night sky and could only guess. Every religion, every philosophy, every system of meaning humans ever built existed in a universe where planets around other stars were theoretical, where we might be alone or we might not be, and there was no way to know. That changed on a specific date, January 9th, 1992. Two astronomers, Alexander Volschan and Dale Frail, published a discovery in the journal Nature. They had detected 2 planets orbiting a pulsar, a rapidly spinning dead star, the compressed remnant of a star that had exploded as a supernova. The planets existed in a radiation environment lethal to any life we can imagine. But they were there, orbiting another star. The universe made planets, And then, on October 6, 1995, Michel Mayor and Didier Queloz announced a planet orbiting 51 Pegasi, a sun-like star 50 light-years away, a gas giant, enormous and scorching, orbiting its star in just 4 days. Not a place for life, but a planet around a star like our sun. Mayor and Queloz received the Nobel Prize in Physics in 2019 for that discovery. And what followed it was one of the fastest paradigm shifts in the history of science. Once we knew how to look, we found them everywhere. This is the thing that strikes me most about the past 30 years of exoplanet science. Not any single discovery, not any particular planet or solar system, but the sheer speed at which the universe revealed its abundance. Before 1995, 0 confirmed exoplanets. By 2002, 100. By 2014, 1,000. By 2020, 4,000. As of mid-2026, the confirmed count in NASA's Exoplanet Archive has surpassed 5,700, with tens of thousands more candidates awaiting verification. 5,700 confirmed worlds orbiting other stars. In 30 years, from 0. And this number represents a tiny sample. The telescopes that found these planets can only detect certain types of planets in certain configurations. Many planets, most planets, are invisible to current technology, not because they don't exist, but because they're too small, too far from their star, or orbit a star that's not oriented favorably relative to Earth. What Kepler, the space telescope that transformed this field, discovered is that the galaxy is fundamentally a planet-making machine. When astronomers took Kepler's data and applied statistical analysis to account for the planets it couldn't see, the estimates were staggering. There are likely more planets in the Milky Way than there are stars. Probably far more. The average star in our galaxy has more than one planet. With 200 to 400 billion stars in the Milky Way, the total planet count reaches into the hundreds of billions. The night sky is not the ceiling of an empty room. It is a window into an ocean of worlds. But what does habitable actually mean? This is where the question becomes more interesting and more personal. Not every planet is a candidate for life. The galaxy produces an enormous variety of worlds. Lava planets orbiting so close to their stars that their surfaces are permanently molten. Gas giants with no solid surface, just deepening layers of compressed hydrogen. Ice worlds far from their suns, frozen to temperatures near absolute zero. Hot Jupiters spinning at dizzying speeds in tight orbits, bathed in radiation. These are all planets, but not, as far as we can tell, places where anything we'd recognize as life could survive. When astronomers talk about habitable worlds, they mean something more specific. They mean planets where liquid water could exist on the surface. This is not because water is the only possible medium for life. It might not be, but it is the only medium we know, the only one we have studied, and the only one we have evidence for across billions of years on Earth. Liquid water requires a specific range of temperatures, above 0 degrees Celsius and below 100 at standard atmospheric pressure. Those temperatures depend primarily on how much energy a planet receives from its star, which depends on distance. The region around a star where surface temperatures allow liquid water is called the habitable zone. The more poetic name, which has stuck, is the Goldilocks zone. Not too hot, not too cold. Earth sits comfortably in our sun's Goldilocks zone. Liquid water has existed on our planet's surface for nearly 4 billion years, and in those 4 billion years, something extraordinary happened. Life arose from chemistry, diversified into millions of forms, eventually developed nervous systems, then consciousness, then astronomy. And then, it started wondering whether the same sequence had played out somewhere else. But here is where the definition had to grow. For decades, the Goldilocks zone was treated as a fairly precise address, A planet needed to orbit at roughly the right distance from roughly the right kind of star. Step outside that zone, and habitability ended. Then we looked more carefully at our own backyard, and the definition started to stretch. Europa is one of Jupiter's moons. It orbits far outside the Sun's habitable zone. Jupiter is 5 times further from the Sun than Earth, and Europa orbits Jupiter. By the traditional definition, Europa should be a frozen, lifeless rock, and on the surface, it is a shell of ice, fractured and ridged, with temperatures around -160 degrees Celsius. But beneath that ice, something unexpected. Jupiter's gravity pulls at Europa with such force, the same force that creates the tides in Earth's oceans, but far more intense, that it flexes and kneads the moon's interior as it orbits. That constant flexing generates heat through friction. And that heat, scientists now believe, keeps a liquid water ocean beneath Europa's icy crust, an ocean that may be deeper than any ocean on Earth, an ocean in contact with a rocky seafloor where hydrothermal vents could provide the chemical energy that sustains life on Earth's deepest ocean floors. No sunlight, no Goldilocks zone, but potentially a warm, salty, chemically active ocean where life could exist. Enceladus, a moon of Saturn, does the same thing and goes further. It actively vents water vapor, ice particles, and organic molecules through cracks in its surface into space. The Cassini spacecraft flew through those plumes and detected hydrogen gas, a chemical sign of hydrothermal activity on the ocean floor beneath the ice. Water, energy, organic chemistry, all present. Everything life on Earth needs, found in a world that should, by old definitions, be dead. These discoveries inside our own solar system changed what habitability means. They expanded the address, and if moons of Jupiter and Saturn can maintain liquid water oceans in conditions far outside the traditional habitable zone, then the number of potentially habitable worlds in the galaxy is not 300 million. It is far larger than that. Then scientists proposed a new kind of world entirely. In 2021, a team of researchers at Cambridge University published a paper that introduced a new concept into astrobiology. They called them Haitian worlds, from hydrogen and ocean. The idea, a class of planets significantly larger than Earth, perhaps 2 to 3 times its radius, with a thick hydrogen-rich atmosphere surrounding a deep global ocean of liquid water. Unlike Earth, which has a relatively thin nitrogen-oxygen atmosphere, a Haitian world's massive hydrogen envelope would act like a heavy blanket, trapping heat and maintaining liquid water across a much wider range of distances from the star. This matters because it extends the habitable zone significantly. A Haitian planet could maintain a liquid ocean even in conditions that would freeze an Earth-like planet solid. It could potentially orbit farther from its star, or orbit a cooler, dimmer star and still be habitable. And because planets in this size range, larger than Earth but smaller than Neptune, turn out to be extremely common in the galaxy, the population of potential Haitian worlds is enormous. The Cambridge team identified a list of candidate Haitian worlds worth investigating. Near the top of that list was a planet called K2-18b, and then JWST looked at K2-18b, and something unexpected happened. K2-18b orbits a red dwarf star about 120 light-years from Earth. It sits in the habitable zone of its star. It is roughly 8.6 times the mass of Earth, solidly in the Haitian size range. It was a candidate, a promising one, but just a candidate. Then, in September 2023, the James Webb Space Telescope published its atmospheric analysis of K2-18b, and the results stopped people in their tracks. JWST detected methane in K2-18b's atmosphere. It detected carbon dioxide. Both are consistent with a Haitian world, an ocean planet covered in a hydrogen-rich atmosphere. But the analysis went further. the team reported a tentative detection of another chemical, dimethyl sulfide, known by its abbreviation DMS. On Earth, dimethyl sulfide is produced almost exclusively by living organisms, primarily by phytoplankton, the microscopic algae that float in the upper layers of the ocean. When these tiny organisms metabolize sulfur compounds, they release DMS as a byproduct. It drifts up into the atmosphere, where it plays a role in cloud formation. On Earth, the presence of DMS in the atmosphere is a biological signal. JWST may have detected that signal on a planet 120 light-years away. I want to be precise about what this means and what it doesn't. The detection of DMS on K2-18b is tentative. The signal sits near the edge of what the telescope can reliably distinguish. Scientists cannot yet rule out an abiotic explanation, a non-biological process that could produce the same chemical. Follow-up observations are needed, and the scientific community appropriately maintains caution. This is not a confirmed detection of life, but it is the closest we have ever come. A chemical that on Earth only living things produce, possibly present in the atmosphere of a world orbiting another star, detected by a telescope launched in 2021 that has been operating for just a few years. The era of guessing whether life exists elsewhere may be giving way to the era of measuring. We find worlds in the dark the way you find someone by listening. The methods astronomers use to detect planets around distant stars are a study in patience and precision. The most productive method is called transit photometry. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. For an Earth-sized planet crossing a Sun-like star, the dimming amounts to roughly 0.008%, less than 1 part in 10,000. Imagine standing a kilometer away from the most powerful lighthouse ever built. Someone holds a marble in front of the beam for 3 hours. That is the magnitude of the signal we are measuring. And yet it works. If the dimming is periodic, happening at regular intervals, it signals an orbiting planet. The time between transits reveals the orbital period. The depth of the dimming reveals the planet's size relative to its star. From a subtle, repeating shadow, we infer an entire world. The second major method is radial velocity. A planet orbiting a star gravitationally tugs at the star as it moves. The star doesn't stay perfectly still, it wobbles. As the star moves fractionally toward and then away from us in its wobble, the wavelength of its light shifts, compressing slightly when approaching, stretching when receding. This Doppler shift is detectable. Measuring it reveals the planet's mass. We do not see these planets directly. We see their shadows crossing their stars. We feel their gravitational whispers in the motion of their suns. We read the light that has filtered through their atmospheres across dozens or hundreds of light years. Every exoplanet we know is a portrait assembled from indirection and inference. The precision required is extraordinary. For many detections, we are measuring a star moving at 2 or 3 meters per second, slower than a brisk jog, from distances of dozens of light years. It is one of the most demanding measurement tasks in the history of science, and it works. Then Kepler arrived and transformed everything. In March 2009, NASA launched a telescope the size of a car and pointed it at a single patch of sky. The Kepler Space Telescope was built to do one thing: stare at approximately 150,000 stars simultaneously for years, without blinking, watching for transits. The planets came pouring in, hundreds in the first year, hundreds more the next. By the time Kepler exhausted its fuel reserves and ended its primary mission in October 2018, it had confirmed 2,662 exoplanets and identified thousands more candidates. It had revealed that rocky planets smaller than Neptune are extremely common. It had found solar systems with 5, 6, 7 planets packed into tight configurations our own solar system doesn't match. It had found planets in habitable zones, multiple planets in habitable zones. Most importantly, Kepler made it possible to do statistics. By studying a known representative sample of stars and counting how often planets appeared, astronomers could extrapolate to the full galaxy. The numbers that came back were stunning even to the scientists running the calculations. Kepler's successor, the Transiting Exoplanet Survey Satellite, TESS, launched in April 2018 and has surveyed nearly the entire sky since then, focusing on the brightest and nearest stars. As of mid-2026, TESS has confirmed hundreds of additional exoplanets. Because TESS targets nearby stars, its planets are the most accessible candidates for follow-up with JWST. The pipeline from discovery to atmospheric characterization is now fully operational. We are not just cataloging planets anymore, we are beginning to read them. The number that changed the question. In 2020, a team of astronomers published a paper in the Proceedings of the National Academy of Sciences. They synthesized Kepler's statistical data and asked, around Sun-like stars in the Milky Way, how many likely host a rocky, Earth-sized planet in the habitable zone? Their answer, approximately 300 million. This is a conservative estimate. It counts only planets around Sun-like FGK stars, not around the red dwarf stars that make up roughly 70% of all stars in the galaxy. Factor in habitable zone planets around red dwarfs, and the number climbs into the billions. Factor in the subsurface oceans on ice moons like Europa and Enceladus, and the definition of habitable expands further still. But even at 300 million, even being conservative, even using only the planets we understand best, the number is almost impossible to hold in the mind. If you spent 1 second thinking about each of those worlds, it would take nearly 10 years. Not 10 years of focused contemplation, 10 years with no sleeping, no eating, no pausing, 10 years at 1 second per world to simply pass through the list. 300 million is not proof that life exists elsewhere. It does not detect a signal or confirm a biosignature, but it does something equally important. It tells us that if life can arise given the right conditions, and we know it can because we are here, then the right conditions are not rare, they are ordinary. They are distributed across our galaxy with a generosity so vast that scarcity can no longer be the argument against life elsewhere, the nearest candidate, and the honesty we owe it. Of all the potentially habitable worlds we know of, the one that sits closest to us is Proxima Centauri b. Orbiting Proxima Centauri, the nearest star to our Sun, at a distance of 4.2 light-years. I want to be honest about the state of this discovery because I think intellectual honesty is part of what makes science worth trusting. The initial confirmation of Proxima Centauri b in 2016 was followed by subsequent analyses that raised questions. Some studies suggested the signal used to detect it might be attributable to activity on the star's surface rather than a planetary body. The debate has not been fully resolved. Many astronomers believe Proxima b likely exists. Others remain uncertain. What I can say is this: even with that uncertainty, the search for habitable planets around Proxima Centauri has not ended. It has deepened. The star remains one of the most intensely studied in the sky precisely because of its proximity. If a habitable planet exists there, we want to know, and the tools to find out are getting better every year. And Proxima Centauri b, real or uncertain, is not the only nearby candidate. In 2023, astronomers announced the discovery of Wolf 1069b, a rocky planet approximately Earth's mass, orbiting in the habitable zone of a red dwarf star called Wolf 1069 about 31 light-years from Earth. tidally locked as most habitable zone planets around red dwarfs are likely to be, with one face permanently toward the star. But simulations suggest that with even a modest atmosphere, the terminator region, the line between permanent day and permanent night, could maintain temperatures where liquid water might exist. 31 light years. In astronomical terms, extraordinarily close. The nearest potentially habitable worlds are not in some remote corner of the galaxy. They are in our immediate stellar neighborhood. They were always here. We simply didn't have eyes good enough to see them. And underneath all of this, the question that science alone cannot answer. I want to end this first part of tonight's journey with something I rarely hear discussed openly in the science, even though I think it is what drives everyone working in this field. If we found life, what would it mean? Not for biology, not for astronomy, for us, for how we understand ourselves, for every framework of meaning that human beings have built over the past several thousand years. The discovery of even simple microbial life on another world, a detection of genuine biological chemistry in a distant atmosphere, confirmed beyond doubt, would be the most significant moment in the history of our species. Not because it would answer the question of how life begins, not because it would tell us anything about intelligence or civilization elsewhere, but because it would tell us that we are not a fluke, that life, the phenomenon we are, is not an accident that happened once on one unremarkable planet around one unremarkable star. It is something the universe does, repeatedly, in multiple places, a property of matter and energy and time when given the right conditions, not an exception to the rules of physics, an expression of them. I find this thought more comforting than frightening. If life is something the universe does, then we are not alone in the deepest sense. Not because there are aliens nearby, not because anyone is coming, but because the process that made us is not a one-time event. It is how the universe works. 300 million chances for that process to have happened again. Let your body be heavy now. Let your thoughts slow to the pace of breathing. Outside, the night is doing what it always does, turning slowly, carrying the stars across the sky. Each one a sun, most of them with planets. Some of those planets sitting in the quiet warmth of their own Goldilocks zone. 300 million worlds. Right now, while you sleep, we are just beginning tonight's journey. The most extraordinary parts still wait ahead. 40 light years from where you are lying right now, there is a star. Not a distant, abstract star at the far edge of some catalog. 40 light years. In the scale of the Milky Way, which stretches 100,000 light years from edge to edge, 40 is nothing. 40 is your neighbor. 40 is close enough that if humanity ever develops the technology to send a probe at a small fraction of the speed of light, we will have an answer back within a human lifetime. That star is called TRAPPIST-1, and orbiting it are 7 planets, all of them roughly the size of Earth. All of them rocky, 3 of them sitting inside the zone where liquid water could exist on the surface. 3 Earth-sized rocky worlds, 1 star, 40 light years away. I want to start there because I think TRAPPIST-1 is the place where this search for habitable worlds stops being abstract and starts being personal. Not because we know life is there, we don't, but because it represents the closest thing we have to a real address, a specific location in the sky where the conditions are right, where the worlds exist, and where the question is no longer theoretical. Settle in, let your body be heavy. We have a long way to travel tonight, and the best parts are still ahead. The system that changed everything we thought we understood about nearby space. For most of human history, the 40 light years surrounding our sun were thought to be largely empty of interesting worlds. We knew there were stars, a few dozen, scattered through that volume of space. But planets, habitable planets, seemed like they might require something special. A sun-like star. the right chemistry, the right distance, a lucky combination of circumstances that might not repeat nearby. Then we looked more carefully at a dim red star 40 light-years away and found 7. TRAPPIST-1 was first targeted by a telescope in Chile called the Transiting Planets and Planetesimals Small Telescope, TRAPPIST, which found 3 orbiting planets in 2016. Then, in February 2017, an international team using NASA's Spitzer Space Telescope published the full picture in the journal Nature. 7 planets, all Earth-sized, all rocky, all orbiting in tight, compact paths around a single star barely 1/10 the mass of our Sun. 7 Earth-sized worlds around one star. No other confirmed system we have found comes close to that. Not in number, not in configuration, not in what it implies. The star itself is classified as an ultra-cool red dwarf. So faint it emits most of its energy in infrared rather than visible light. It is not the kind of star you can see with the naked eye from Earth. You would need a telescope to pick it out of the sky, and yet it hosts more potentially habitable worlds than any other system within 40 light-years. The universe does not arrange things the way we expect. The 3 planets in or near the habitable zone are TRAPPIST-1e, 1f, and 1g. Of these, TRAPPIST-1e attracts the most attention from astrobiologists. Its orbit places it to receive roughly the same amount of energy from TRAPPIST-1 that Earth receives from the Sun. Its density measurements, derived from the gravitational interactions between the 7 tightly packed planets, suggest it is a rocky body, not a gas world. And the star has been burning steadily for an estimated 7 to 8 billion years, though with significant uncertainty in that figure spanning roughly 5 to 10 billion years. 5 to 10 billion years of stability, compared to Earth's 4.5 billion years of existence. Close your eyes for a moment and try to imagine standing there, TRAPPIST-1e, a world 40 light-years from Earth. The sky above you would be a different sky. TRAPPIST-1 is a red dwarf. Its light redder and dimmer than our Sun. The daylight on TRAPPIST-1e, if the planet has an atmosphere to scatter that light, might appear rust-colored or amber rather than blue. The star would appear slightly larger in the sky than our Sun does from Earth, burning a deep, steady red-orange. You would likely be standing near the terminator, the line between the planet's permanent day side and its permanent night side. TRAPPIST-1e is almost certainly tidally locked, meaning one face toward the star always, one face toward the dark always. On the terminator, the star hangs permanently near the horizon, never rising, never setting, a fixed point at the edge of the world. Here, winds from the day side carry warmth toward the night side. Climate models suggest that with even a modest atmosphere, the terminator region could maintain temperatures where liquid water might persist. Not scorching like the noon point of the day side, not frozen like the deep night. Something in between. Something that, on a map of possibilities, lies in the range where chemistry can do extraordinary things. Now here is what I find most staggering about TRAPPIST-1e. That star is older than our Sun by at least 2 to 3 billion years. If life began on TRAPPIST-1e at roughly the same pace it began on Earth, and we have no reason to think it would be dramatically faster or slower, then whatever is on that planet right now is not where Earth is in 2026. It is where Earth will be in 4 or 5 billion years. I do not know what 4 billion years of additional biological evolution produces. Neither does anyone else. We can barely imagine what Earth's own biosphere will look like in 10,000 years. What exists on a potentially habitable world that has had the same process running for 3 billion years longer than we have. I genuinely cannot form a mental picture of it. It exceeds every framework I have, and it is 40 light years away. The complication we owe TRAPPIST-1 honesty about, there is a legitimate concern about red dwarf systems, and I want to address it directly rather than burying it in the fine print. Red dwarfs like TRAPPIST-1 are active. They flare. Periodically, they release intense bursts of ultraviolet and X-ray radiation, far more violent than our sun's flares, relative to the star's size. For planets orbiting as close as the TRAPPIST worlds must to receive enough warmth, these flares bombard the surface and upper atmosphere repeatedly over billions of years. If a planet cannot maintain an atmosphere against this erosion, it becomes a bare rock. No atmosphere, no liquid water, no possibility of surface life as we understand it. This is a real constraint, and it is exactly what JWST has been testing. In 2023, the James Webb Space Telescope published its first results on TRAPPIST-1b and TRAPPIST-1c, the two innermost planets. What JWST measured was thermal emission, the heat radiating from each planet's surface. For a planet with a thick atmosphere, heat absorbed on the day side gets distributed around the planet by atmospheric circulation. The night side would be warmer than it would be for a bare rock. TRAPPIST-1b showed very little thermal redistribution. The data is most consistent with a bare rock, or at most a thin atmosphere insufficient to carry heat. TRAPPIST-1c produced a similar result, far less carbon dioxide than a Venus-like world would have, suggesting a sparse or absent atmosphere. Two bare rocks. Disappointing. But TRAPPIST-1b and 1c are not in the habitable zone. They orbit closer to the star, where radiation pressure is higher and atmospheric stripping is faster. Their failure to retain atmospheres does not necessarily predict what TRAPPIST-1e, orbiting further out in the protected habitable zone, looks like. The planet most analogous to Earth in this system has not yet been directly characterized by JWST. Those observations are ongoing. They require many transits accumulated over time to build sufficient sensitivity. The answer about TRAPPIST-1e is coming. We simply do not have it yet. I think the right posture toward these JWST results is not despair, but the patient suspension of judgment. We are reading other worlds in real time. Not every page will contain what we hope to find, but we are reading. In November of 1961, a young astronomer wrote an equation on a blackboard. His name was Frank Drake. He was at the National Radio Astronomy Observatory in Greenbank, West Virginia, preparing for what would become the first scientific conference on the search for extraterrestrial intelligence. 11 colleagues gathered with him, including Carl Sagan, who was 27 years old. Drake had a problem. The conference was meant to organize the scientific thinking around whether detectable civilizations existed elsewhere in the galaxy, but the scope of the question was enormous. Every variable was unknown. Every assumption could be challenged. So he wrote an equation, not to answer the question, but to map the ignorance. To break an impossible question into a series of smaller, harder, more tractable questions, each one a research program rather than a guess. The equation multiplied a chain of probabilities together, each one asking, of all the worlds that pass this previous filter, how many survive the next? The first term, how many new stars form in the Milky Way each year? Now we know this reasonably well, roughly 1 to 3 new stars per year. The second term, of those stars, what fraction have planetary systems? When Drake first wrote it, this was completely unknown. We now know it is close to 1. Nearly every star has planets. The third term, for each star with planets, how many sit in the habitable zone? Kepler gave us real statistics here. The 300 million figure we began tonight with is essentially the product of these first 3 terms applied across the galaxy. Then the equation enters the territory where our data runs out. The fourth term, of planets where life could arise, what fraction actually develop it? On Earth, life appeared within a few 100 million years of the surface cooling enough to allow liquid water. That happened either because, given the right chemistry and energy and time, life is nearly inevitable, or because Earth was extraordinarily lucky. and we are the rare survivors in a vast graveyard of sterile worlds. We cannot tell which because we have only one example. The honest answer is that this term could be close to 1 or close to 0. The fifth term, of worlds with life, what fraction develop intelligence? Multicellular life existed on Earth for more than 500 million years before anything resembling intelligence appeared. The fossil record suggests intelligence is not an automatic outcome of evolution. It required specific pressures, specific body plans, specific environmental conditions. It could be rare even where life itself is common. The sixth term, of intelligent civilizations, what fraction developed the technology and the inclination to communicate across interstellar distances? The seventh term, L. How long does a communicating civilization persist? If the average civilization broadcasts for 100 years before going silent, through catastrophe or transformation or simply choosing to direct its energy elsewhere, then even a galaxy full of civilizations might produce only a handful of simultaneous overlaps. We have been producing detectable radio signals for approximately 100 years. L for us is still being written. Drake's original estimate, plugging in optimistic numbers, was roughly 10 detectable civilizations in the Milky Way at any given time. Modern estimates span a range from less than 1, we may be genuinely alone, to millions. The equation does not resolve the question. It reveals, with mathematical clarity, exactly where our ignorance lives. But here is an angle I rarely hear discussed, and I think it changes the picture. We have been searching for radio signals for 65 years, specifically for the kind of radio signals that civilizations on Earth were broadcasting in the mid-20th century. AM and FM transmissions, radar pulses, television carrier waves. But consider what has happened to Earth's own radio signature in that same time. In the 1950s, Earth was broadcasting broadly into space. Television and radio towers sent signals in all directions. Our radio signature was strong and growing. But over the following decades, something changed. Broadcasting moved to cable. Telecommunications moved to fiber. Satellites became directional, beaming narrowly rather than broadcasting widely. And now, in the 2020s, much of our communication travels through systems that leak very little into space at all. Earth is becoming, by the metric of omnidirectional radio emission, quieter. A civilization monitoring us from 100 light-years away, detecting the radio leakage from mid-20th century Earth, would conclude that a technological civilization existed here. A civilization detecting us now might find a faint and ambiguous signal, even though we have more technology, more infrastructure, and more intelligence than we did 70 years ago. If this is happening to us, it may be happening to others. A civilization that transitioned through its radio era 500 years ago might now be invisible to our current listening strategy, not because it collapsed or went silent, but because it simply moved on to forms of communication that don't leak into space the same way. We may be listening in the wrong language, looking for a signal that more advanced civilizations stopped making centuries ago. This is not a reason to stop searching. It is a reason to search in more than one way. We have been searching for 65 years in the oldest possible form of patience. Project Ozma was the beginning. In the spring of 1960, Frank Drake pointed the 85-foot radio telescope at Green Bank at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for approximately 150 hours across 2 months. The name came from the fictional kingdom in L. Frank Baum's Oz books, a place very far away, difficult to reach, and populated by strange and exotic beings. He detected nothing from another civilization, but the act of listening had begun. What followed was decades of intermittent, underfunded effort. The scientific community was broadly skeptical. Congress defunded NASA's SETI program in 1993, with one senator referring to it dismissively as the Great Martian Chase. The search continued through private funding and the stubborn commitment of scientists who believed the question was worth asking regardless of institutional support. In 2015, that changed. Russian-Israeli billionaire Yuri Milner announced the Breakthrough Listen initiative, $100 million over 10 years to fund the most sensitive and comprehensive SETI search in history. Breakthrough Listen operates the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, scanning 1 million nearby stars and the centers of 100 galaxies. As of mid-2026, it has produced no confirmed detection, but it is listening with more precision across a wider frequency range than anything before it. Several groups also now scan the sky for laser pulses, brief, intense flashes of light from a powerful directed beam, invisible to the naked eye but distinguishable from natural sources by a spectrograph. This is optical SETI. The logic: if you wanted to signal across interstellar distances with minimum energy, a highly focused laser pulse might be more efficient than omnidirectional radio. Someone who had moved past the radio era might be signaling in light instead. No confirmed signal has ever been detected through any of these methods. But on one summer night in 1977, something happened that has never been fully explained. The wow signal is one of the strangest 72 seconds in the history of science. On the night of August 15, 1977, the Big Ear Radio Telescope at Ohio State University was conducting a routine SETI survey. The data was not monitored in real time. It was printed on paper and reviewed later by a volunteer astronomer named Jerry Eman. Several days after the observation, Eman was going through the printout when he saw something in the data, a burst of signal that rose sharply over several minutes, peaked, then declined. Exactly the pattern you would expect from a signal emanating from a fixed point in space as the telescope's beam swept across the sky during Earth's rotation. The signal lasted 72 seconds, which is precisely the amount of time Big Ear's narrow beam takes to cross a fixed position in the sky. It was centered at 1,420 megahertz, the frequency of neutral hydrogen, the most abundant element in the universe, and the frequency that SETI researchers had designated decades earlier as the most logical channel for interstellar communication. The reasoning: any technological civilization in the galaxy would know hydrogen, would know its spectral frequency, and would understand why this particular wavelength stands apart from others. The signal's strength was approximately 30 times the background noise level. Strong, clearly anomalous. Unlike anything else in the data, Jerry Eman circled the numbers with a red pen and wrote in the margin a single word: wow. The name stuck. 65 years of follow-up observations of the same region of sky have detected nothing similar. The wow signal has never repeated. It has never been explained by any confirmed natural phenomenon. No satellite, no ground-based interference, no known astrophysical process fits the profile cleanly. It has not been confirmed as extraterrestrial in origin, but it has also never been convincingly debunked. What we know is this: for 72 seconds, a radio telescope detected something with every characteristic SETI researchers would hope to find in a genuine signal from another civilization, at the right frequency, in the right pattern, strong enough to stand out clearly from the noise. And then it was gone. I sit with the wow signal differently than I sit with most unresolved scientific questions, not with frustration at the lack of an answer, with something quieter, the reminder that the universe is not obligated to repeat itself for our convenience, that the most significant thing that has ever happened might last 72 seconds, happen on a summer night in Ohio while the astronomer is at home, and be found 4 days later on a sheet of paper. If it was a signal, it is the closest we have come. If it was not, it is still extraordinary, an anomaly so precisely shaped that the question it raises has never been put to rest. Not knowing is its own strange kind of gift. What life looks like when read from 100 light-years away. When astronomers search for signs of life on distant worlds, they are reading light, not listening for voices, not waiting for a ship to arrive. Reading chemistry encoded in the wavelengths of starlight that is filtered through a planet's atmosphere. Every molecule absorbs and emits light at specific wavelengths, a spectral fingerprint as unique and precise as a musical note. When a planet transits its star, some of the star's light passes through the outer layers of the planet's atmosphere before reaching us. Different molecules leave different signatures in that light. A spectrograph records which wavelengths were absorbed. From that pattern, we reconstruct the atmospheric chemistry of a world we will never visit. This is transmission spectroscopy, and JWST performs it with sensitivity no previous instrument could approach. On Earth, the atmosphere carries chemicals that would be impossible to explain without life. Oxygen makes up 21% of the air. Oxygen is chemically reactive. It oxidizes metals, breaks down organics, binds to rocks. Without continuous replenishment, the oxygen in Earth's atmosphere would disappear within a few million years. The only thing producing it at planetary scale is photosynthesis. Observe Earth from 100 light-years with a powerful enough spectrograph, detect the oxygen, and you know something biological is running on the surface. Methane is another biosignature. On Earth, methanogenic microbes, archaea, living in oxygen-poor sediments, in swamps, in animal guts, in deep ocean floors, produce vast quantities of methane. Without biology, methane in an oxygen-rich atmosphere would react away within years. The simultaneous presence of oxygen and methane at detectable levels is considered one of the strongest possible biosignature combinations precisely because they react with each other. They should not coexist. They require explanation. Nitrous oxide, produced by nitrogen cycling bacteria, is another marker. Dimethyl sulfide, which JWST tentatively detected at K2-18b, comes almost exclusively from ocean phytoplankton. And now there is a new category we have started to consider. In recent years, a small but serious group of researchers has proposed searching not just for biosignatures, chemical signs of life, but for something they call technosignatures, chemical signs of technology. The logic is straightforward. Earth's industrial civilization has changed the composition of our atmosphere in ways that would be detectable from space. We emit fluorinated gases, hydrofluorocarbons, nitrogen trifluoride, sulfur hexafluoride, that are used in semiconductor manufacturing, refrigeration systems, and industrial processes. These molecules are not produced by any known natural process. They have no abiotic source. If they appear in a planetary spectrum, they indicate industry. Researchers at Harvard and elsewhere have calculated that JWST, with sufficient observation time, could potentially detect certain industrial fluorinated gases in the atmospheres of nearby planets if they were present at concentrations comparable to Earth's current levels. It would require many transits. The signal would be faint, but it is, in principle, detectable. Earth is already broadcasting its industrial signature into space. The light that left Earth 40 years ago, now reaching TRAPPIST-1, carries the chemical fingerprints of our factories, our refrigerators, our semiconductor fabs. Someone there with JWST equivalent technology pointed at us might already be reading what we are. The thought is not comfortable, but it is interesting. JWST is doing this work right now, tonight, while you listen. The telescope has been operational since mid-2022. In the years since, it has observed dozens of exoplanet atmospheres. K2-18b, the TRAPPIST-1 worlds, LHS 114OB, a rocky super-Earth in the habitable zone of a red dwarf about 41 light-years from Earth, one of the most promising current targets. TOI-700D and TOI-700E. Two potentially habitable worlds orbiting the same red dwarf star 100 light-years away, both discovered by TESS and now available for atmospheric characterization. Each observation is a transit. Each transit adds a thin layer of data to what we know about a particular planet's atmosphere. For most targets, a single transit is not enough. The signal is too faint relative to the noise. You need tens of transits accumulated over months or years before the picture becomes clear. JWST has a planned operational lifetime of at least 20 years, potentially longer. Each year it operates adds more transits, more sensitivity, more depth to our atmospheric portraits of other worlds. The pipeline is not going to produce a dramatic single announcement on a specific morning. It is going to produce a growing body of evidence, building slowly and then not slowly, until a pattern emerges that cannot be explained without life. That pattern may emerge in the next 5 years, or the next 15, or perhaps never in our lifetimes. But the process is working. For the first time in the history of astronomy, we are not just finding planets, we are reading them. And somewhere underneath all of this measurement, a quieter truth sits. Every instrument we have built, every frequency we have listened to, every atmospheric spectrum we have analyzed, these are all expressions of the same impulse that sent Project Ozma's beam toward Tau Ceti in 1960, the impulse to find out whether we are alone, not because it would change our daily lives, not because it would solve an immediate problem, but because it would change what we understand ourselves to be. A species in a lifeless universe is one thing. A species in a universe that makes life in multiple places, that does this regularly as part of how matter and energy and time work, is something else entirely. The distinction is not scientific, it is philosophical. It is about what kind of story we are living in. I think about the people who built Project Ozma with essentially no budget, pointed a radio telescope at a few stars, and listened. Not because they expected to find something, but because the question demanded to be asked. The act of asking, they believed, was itself worthwhile, whether or not the answer arrived. Tonight, we have covered a lot of ground. 7 worlds 40 light-years away, an equation that maps the shape of our ignorance. 65 years of listening across frequencies chosen for their logic. A 72-second mystery written in red ink in the margin of a printout. Chemical fingerprints of life and industry, potentially readable across interstellar distances. The question is still open. The search is still running. And the universe, vast and quiet and full of worlds, continues to do whatever it is going to do, regardless of whether we are awake or asleep to see it. Let your breathing slow now. Let the facts settle from the surface of your mind down into something deeper. You do not need to hold all of this tonight. It will be here when you need it. We still have one more part of the journey ahead, the deepest part, the part that asks what it would actually mean if the answer were yes. But that is for later. For now, rest. The night is deep now. You have been traveling for a long time. The facts from the earlier parts of tonight's journey, the 7 worlds 40 light-years away, the telescope reading chemistry across interstellar distances, the 72-second signal from 1977 that no one has ever explained. Those have had time to settle. They are no longer information. They are background, a new landscape in which the next question can be asked. And the next question is the one that has been waiting underneath all the others since the beginning. We have established that the galaxy is full of planets, that habitable worlds number in the hundreds of millions, that the chemistry of life, carbon, water, energy, time, is distributed across the cosmos with what looks, from where we stand, like generosity. We have established that we have the tools now to begin reading the atmospheres of those worlds, that the search is no longer theoretical. Given all of that, where is everybody? Not in the poetic sense, not as a wistful thought before sleep, literally. If the universe makes planets so readily, and if habitable planets are so common, And if even a fraction of them develop life, and if even a fraction of that life becomes intelligent and technological, then by the math, the galaxy should be full of civilizations, old ones, civilizations with billions of years of head start on us, civilizations that should have had time, even traveling slowly, to spread signals or structures or some recognizable trace across the entire Milky Way. And yet, quiet. The telescopes listen. The sky gives nothing back. Tonight we are going to sit with that silence and understand what it might mean. In the summer of 1950, a physicist asked the question that started everything. His name was Enrico Fermi, Nobel Prize winner, one of the architects of the Manhattan Project, one of the most formidable scientific minds of the 20th century. He was having lunch at Los Alamos National Laboratory in New Mexico with 3 colleagues, Edward Teller, Herbert York, and Emil Konopinski. The conversation had been light, wandering from the news of the day, a cartoon in the New Yorker about aliens stealing New York City's trash cans, into the broader territory of UFO reports that were popular in the press at the time. The men were laughing, and then Fermi went quiet. And then, in the middle of lunch, he asked, "But where is everybody?" The people around the table knew immediately what he meant. Not the cartoon, not the newspaper reports, something much larger. If the universe is 13 billion years old, if stars like our sun are spread across hundreds of billions of systems, if even a small fraction of those systems produced technological civilizations with even a fraction of our ambition, then somewhere, given billions of years of head start, something should have arisen capable of leaving a mark we could find. Herbert York recorded the moment in his memoir decades later. What struck him was not the question itself, but how quickly everyone at the table understood what Fermi was actually asking, as if the thought had been waiting in all of them, unvoiced, and Fermi had simply been the one to say it aloud. This is what we now call the Fermi Paradox, not a logical paradox, strictly speaking, a mismatch between what the mathematics of a planet-rich universe seems to predict and what our actual observations of the sky have so far found. The mathematics of the problem deserves a moment. The Milky Way is roughly 100,000 light-years across. Our galaxy is approximately 13 billion years old, nearly 3 times the age of Earth. There are between 200 and 400 billion stars in it, the majority of them hosting planets. Now consider, at 1% of the speed of light, slow by science fiction standards but at least physically imaginable, you cross 1,000 light-years in 100,000 years. Traveling and colonizing, leapfrogging from star to star, even at this modest pace, a civilization could permeate the entire Milky Way in well under 100 million years. 100 million years sounds enormous, but the galaxy is 130 times that age. In the span of galactic history, 100 million years is a Tuesday afternoon. If any civilization anywhere in our galaxy's 13 billion year history had reached the point of interstellar travel and then continued expanding, we would expect to find evidence of it. Signals, megastructures visible to our telescopes, modified star systems, something. Instead, the stars burn in their old patterns. The radio telescopes listen. Nothing speaks back. The silence is the mystery, and the attempts to explain it form one of the most unsettling branches of modern science. The first explanation is the one I think we move past too quickly. Perhaps life itself is the rare step. For years, the origin of life seemed almost inevitable. Given liquid water, the right chemistry, an energy source, and enough time, surely biology would find a way. But the more carefully scientists look at the transition from complex organic chemistry to self-replicating, metabolizing biological systems, the less certain inevitable appears. The RNA world hypothesis, the various theories about deep-sea hydrothermal vents, the panspermia models, these are all serious proposals, but none of them is established. We do not actually know how life began on Earth. We know it happened. We know it happened relatively quickly after the planet cooled, but the mechanism, the specific chain of events, the exact set of conditions, these remain genuinely unknown. And if the origin of life requires conditions or a sequence of events more improbable than we assume, then the galaxy could be full of habitable planets that simply never crossed the threshold. Peter Ward and Joe Brownlee argued something stronger in their 2000 book, Rare Earth. That even if life arises readily given the right conditions, Earth may be extraordinarily unusual in having those conditions simultaneously. A large stabilizing moon preventing wild swings in axial tilt. Jupiter in the outer solar system acting as a gravitational shield, deflecting many of the large impactors that would otherwise repeatedly sterilize the inner planets. A location in the outer arm of the galaxy, away from the dense, radiation-intense center. Plate tectonics regulating the carbon cycle over billions of years, with a consistency that keeps temperatures habitable. Strip away any one of these factors, and Earth's 4 billion-year story of continuous life may never have run. Perhaps the silence is not because life stopped somewhere down the road. Perhaps it never started in most places at all. But I find a different explanation more compelling and more unsettling. Let us say life is common. Let us say it arises wherever the chemistry and energy are right, readily, reliably, the way water finds cracks in rock. Let us say the galaxy is teeming with microbial biospheres on ocean floors and in warm subsurface environments on worlds we haven't yet visited. Even then, the Fermi Paradox remains. Because what has not called us, what has not broadcast its existence, is not simple life. It is technological civilization, intelligence, minds capable of building radio telescopes and sending signals across interstellar distances. And here, perhaps, is the filter. On Earth, multicellular life took over 3 billion years to appear after single cells. Nervous systems took hundreds of millions of years more. Language, tool use, abstract reasoning, these emerged only in the last 2 to 3 million years of a 4 billion year story. Intelligence, in any meaningful sense, has existed for less than 0.1% of life's history on this planet. Perhaps that ratio is typical. Perhaps life fills countless oceans and subsurfaces across the galaxy, and the step from alive to aware is so difficult, so contingent, so dependent on specific evolutionary pressures and body plans and environmental conditions that intelligence is genuinely rare even where biology flourishes. A galaxy teeming with microbes but nearly empty of minds would be silent in exactly the way we observe. Then there is the possibility that intelligence is not rare, but civilizations are brief. Technology advances faster than wisdom. This is not a rhetorical point. It is an observable pattern in our own history. We developed nuclear weapons before we developed reliable global governance of nuclear weapons. We are developing artificial intelligence faster than we are developing frameworks to manage its risks. Climate change has outpaced coordinated global response for decades. The window between technological enough to communicate across interstellar distances and technological enough to destroy ourselves may be very narrow. And if most civilizations do not make it through that window, if the average lifespan of a communicating civilization is a few hundred years rather than millions, then even a galaxy full of civilizations could produce very few that exist simultaneously within communication range of each other. We have been producing detectable radio signals for roughly 100 years. The question of whether we will produce them for another 100 is not settled. There are stranger explanations, some hopeful, some darker. Astronomer John Ball proposed in 1973 what he called the zoo hypothesis, that advanced civilizations deliberately avoid contact with developing ones. The way a field biologist observes an ecosystem without disturbing it. the way a more cautious traveler keeps distance from a culture not yet ready for contact. We are being watched, perhaps, studied, even, but not spoken to. By design, by policy, maintained across all civilizations, advanced enough to have the choice. I find the zoo hypothesis intriguing but logically fragile. For the silence to hold, the policy of non-contact would need to be universal. Every civilization in the galaxy, independently developed and independently motivated, would need to reach the same conclusion and maintain it across millions of years. A single rogue civilization, one culture of billions that disagrees with the consensus, one explorer too curious to stay silent, breaks the silence for everyone. Then there is an idea that came not from astronomy but from fiction, and which has been taken seriously enough that physicists have written papers engaging with it. In his 2008 novel The Dark Forest, Chinese writer Liu Cixin proposed a thought experiment that he called the Dark Forest hypothesis. To be clear, this is not an established scientific theory. It is a logical framework that emerged from science fiction and that some researchers have found coherent enough to examine seriously. The logic runs like this. Every civilization requires resources. Resources are finite. Any civilization advanced enough to reach the stars is also advanced enough to destroy other civilizations. In a universe where detection means vulnerability and trust is impossible to verify across interstellar distances, the rational strategy for any civilization aware of this dynamic is to stay silent, listen carefully, and eliminate any civilization whose existence it discovers before being eliminated itself. The silence of the sky, in this framing, is not the quiet of an empty room. It is the quiet of a room full of hunters, each one perfectly still, waiting to see who moves first. I want to be careful here. This is a thought experiment, not a conclusion. The universe may not work this way at all. It may be full of civilizations that cooperate, that help each other, that broadcast freely. We have no evidence for the dark forest model, but I cannot find a logically airtight reason to dismiss it entirely, and that uncertainty is, I think, worth sitting with honestly. And then there is the most important idea of all, the one with real teeth. In 1998, economist Robin Hanson published a paper titled The Great Filter, Are We Almost Past It? He was trying to find a single framework that could explain the silence regardless of which specific explanation was correct. His insight, somewhere on the path between dead chemistry and galaxy-spanning civilization, there must be a step so improbable, so catastrophically difficult, that almost nothing makes it through. He called this the Great Filter. It could be the origin of life, the development of complex cells, the emergence of intelligence, the survival of a technological civilization through its most dangerous period, or something else entirely, not yet identified. The Great Filter exists. The silence confirms it. Something stops nearly everything. Then Hansen asked the question that I consider one of the most important a person can seriously engage with in the 21st century. Is the Great Filter behind us? Or is it ahead? If behind us, if the nearly impossible step was the origin of life, or the leap from prokaryotes to complex cells, or the emergence of intelligence, then we may be genuinely rare, among the first to make it through. The road forward is uncertain, but it is not pre-blocked by some inevitable destruction waiting further along. If ahead, if the rare step is something that technological civilizations must face and almost all fail, then the silence tells us something deeply personal about our own future. Somewhere between where we are now and where we would need to be to become a lasting interstellar presence, there is something that kills nearly everything that reaches it. Nuclear weapons, climate change, artificial intelligence, engineered biology. Some technology not yet invented that will seem, in retrospect, like the obvious candidate. something we are possibly approaching right now, without knowing we are approaching it. Now, here is the part that turns the intuition around completely. Hansen points out that every piece of good news about the prevalence of life in the universe is simultaneously evidence that the great filter lies ahead of us rather than behind. If we discover that life arose on Mars, if JWST confirms a biosignature on a distant ocean world, if we find that life is common, that it emerges readily wherever conditions allow, then the filter cannot be at the origin of life. It must be somewhere further down the road, somewhere we have not yet reached. The better news for life in the universe, the worse news potentially for us. This is why I think the search for life elsewhere is not simply a scientific project. It carries existential weight. Every positive result narrows our options about which kind of universe we inhabit. Now imagine a specific morning. You are somewhere ordinary. Maybe you are having coffee. Maybe you are on a commute or at a desk or still in bed reaching for your phone. A notification arrives, not a rumor, not a preliminary announcement. A joint statement from NASA, ESA, and an international consortium of astronomers, backed by multiple independent research groups, announcing that JWST has detected a confirmed, reproducible atmospheric biosignature on a planet 85 light-years from Earth. Oxygen and methane coexisting in quantities that cannot be explained by any known abiotic process. Confirmed, peer-reviewed, accepted. What do you feel? I have thought about this more than I probably should, and what I keep arriving at is not what I expected, not pure elation, something more complicated, a kind of vertigo, as if the floor of the world has shifted very slightly and will never be exactly level again. Because in that moment, everything that has been uncertain becomes settled. We are not alone. Life is not a one-time accident. Whatever we are, this improbable accumulation of chemistry and memory and awareness is not unique. It is a thing the universe does, repeatedly, in multiple locations, a property of matter and energy given sufficient time, not a miracle that happened once. The theological implications would be enormous and different for different traditions. The philosophical implications would take generations to work through fully, but the immediate human experience, I suspect, would be something quieter, a stillness, a recalibration, the sense of standing at the edge of a new map. And then life would continue. Coffee would go cold. Commutes would resume. The machinery of daily existence would absorb even this, as it always does, and carry on. But something would have changed permanently and irreversibly. We would know what kind of universe we live in. There is a problem of time that no technology can solve. Even if we find a biosignature, even if we detect a signal, even if we confirm beyond any doubt that life exists on a world 100 light-years away, we are reading that world as it was 100 years ago. The light we detect tonight left its source in 1926. The atmosphere we are characterizing is the atmosphere of a planet as it existed when humans had not yet reached the moon, when penicillin had not been discovered. Whatever is there now, whatever evolved or changed or ended in the century since that light departed, we do not and cannot know. If there were a civilization on that world sending signals today, we would not receive them for 100 years, and our response would take another 100 years to reach them. A conversation would unfold over centuries with no guarantee that either party would survive to complete it. For stars 1,000 light-years away, we see them as they were in the year 1026. A civilization we might detect there could be gone by now, collapsed, transformed, moved beyond any form we could recognize, or it could be thriving, completely unaware that someone 1,000 years in its future is looking at an old photograph of its sky, The universe we observe is always the universe as it was, layered in time by the speed of light, so that looking outward means looking backward. Every exoplanet we study is an artifact of its own past. Every signal we receive is a message from history, and still we look. Because looking is what we can do, and doing it honestly, knowing its limitations, knowing we are reading light that is already old, is the most rigorous form of curiosity available to us. Here is a question the scientific community has not agreed on, and I think it deserves more attention than it gets. Given the Fermi Paradox, given the possibility that the Great Filter lies ahead, should we be broadcasting our own existence into space? We did not ask this question before we started. In November of 1974, the Arecibo radio telescope in Puerto Rico beamed a 3-minute message into space, composed by Frank Drake and Carl Sagan. It encoded mathematical information, the structure of DNA, a diagram of a human figure, a map of our solar system. It was aimed at M13, a globular star cluster 25,000 light-years away. The message has been traveling since the moment it was sent. It will not arrive for another 24,975 years. In 1977, we attached a gold-plated copper disc to the Voyager spacecraft, the Golden Record, containing greetings in 55 languages, music from across human cultures, the sounds of ocean waves and wind, and the laughter of a child. Voyager 1 now travels roughly 25 billion kilometers from Earth. In approximately 40,000 years, it will pass within a few light years of a star called Gliese 445. Still traveling, carrying our voices. These acts were beautiful. I genuinely believe that. But they were made without serious debate about whether they were wise. Stephen Hawking, before he died in 2018, was explicit about his concern. Meeting an advanced civilization could be like the Native Americans meeting Columbus, he said, and that didn't turn out so well. His view was that an advanced civilization with the technology to reach us would also have the technology to exploit or eliminate us, and that advertising our location was not obviously a good idea. The debate within SETI continues. Some researchers argue that Earth has already been leaking radio signals for a century, and any civilization capable of responding already knows we are here. Others argue that directed, powerful transmissions are categorically different from leakage and should require something approaching global consensus before we send them. No global consensus exists. Some groups have already sent targeted transmissions without one. I am not telling you what to think about this. I am not sure what I think about it, but it strikes me as one of the most significant policy questions our species has never seriously organized around. The decision to announce ourselves to the cosmos, if we are making it, and we are, should probably involve more than a few research groups acting independently. And then, in December of 2020, the telescope that sent the Arecibo message collapsed. One of its support cables failed without warning. The 900-ton receiver platform, suspended above the 305-meter dish, fell. In seconds, the largest radio telescope in the world for 53 years, the instrument that had broadcast humanity's first deliberate interstellar message, was gone. I have watched the footage of it collapsing many times, and each time I feel something I find difficult to name precisely. Not just loss, something more like the particular poignancy of things that carry meaning ending without ceremony. The telescope that Sagan used to teach the world about space, the instrument that sent our voice into the dark, ended on a Tuesday in December without warning in a few seconds of falling cable. The Golden Record is still out there. Voyager 1 is still moving, somewhere beyond the edge of the heliosphere in the cold space between stars. The message is still traveling. The voice is still in the dark. What that means, whether it will ever be heard, whether hearing would matter, whether the universe cares about gold-plated discs carrying the sound of rain, I cannot tell you. But I think Carl Sagan was right about what those acts actually were. Not practical attempts at communication across distances too vast for any practical response in a human lifetime. Something else, a ceremony, a declaration, a species saying, "We know we are probably not alone, we cannot prove it yet, but we have decided to announce ourselves anyway." Because announcing ourselves is an act of hope, and hope, whatever else it is what makes us who we are. Why the wondering matters, not as sentiment, but as a fact about what we are. I want to end tonight not with a conclusion, because there is no conclusion yet. There may not be one in our lifetimes. The search is ongoing. The sky is still quiet. JWST is still reading atmospheres, one transit at a time, building its portrait of distant worlds with the patience of an instrument that does not get tired. But I have come to believe something I cannot prove and cannot stop believing. The universe that produced us, that evolved chemistry into biology, biology into nervous systems into language, language into a species that builds telescopes and points them at the stars and asks whether anyone else is there, is not indifferent to its own contents. It made something in us that can look back at it and wonder. That is either a coincidence or it is something else, something we don't yet have the right word for. And if the same process has run elsewhere, if there are other minds, somewhere among the 300 million, looking up at their own strange sky and asking the same question we have been asking tonight, then the wondering connects us to them. Not because we can communicate, the distances are too large, the time delays too long, but because the act of asking quietly in the dark, "Is there anyone there?" is itself a form of kinship with anyone, anywhere, who has ever asked the same. Come home now. The journey is over and the night has held you well. We traveled 40 light years to a dim red star with 7 Earth-sized worlds. We sat with an equation that maps the shape of our ignorance about the cosmos. We listened to the Fermi Paradox and its possible answers, some hopeful, some chilling, all honest. We thought about a great filter that might lie behind us or ahead of us, and what finding simple life elsewhere would actually imply. We imagined the morning of the most significant announcement in human history. We let the Arecibo message travel, and the golden record travel, and the question travel into a dark that gives no guarantee of an answer. And now you are here, in a room, on a planet that is, as far as we currently know, the only one in the observable universe where something has been awake long enough to ask all of this. The night sky outside your window contains every star we have discussed. TRAPPIST-1 is out there in the direction of Aquarius. K218b is out there, 120 light years in the dark, the region where the wow signal came from lies somewhere below your horizon, but it will rise by morning. The stars you cannot see are doing what stars always do, burning through their fuel, holding their planets in their orbits, illuminating surfaces we have not named. You don't need to hold all of this tonight. You carried it. That is enough. Let your body be completely still. Let your breathing come and go without effort. Let the 300 million worlds continue existing in the dark the way they do, whether anyone thinks about them or not. Quietly, in their orbits, spending another night under their own strange skies. We are still looking, the telescopes are still turning, and somewhere out there, if the science and the hope are both right, something might be looking back. Sleep well.